all right, let's get started. Give everybody a second to sit down. So this class presentation is about the Great Heat Pump Revolt of 2026. As you see from my sign right there, we have a technician saying, but they promised me it would work, right? And we're going to get into why that technician has the woes staring him in the face. So who's going to help me out here is Russ King. He is the CEO of Coded Energy. If you've used the software Quick Model, that's Mr. Russ King right there and his son who have that program. And Steve Rogers, who is the president of the Energy Conservatory. So we're going to facilitate kind of a conversation where I'll be kind of walking the crowd a little bit. We're going to try to make this thing lively because it's the end of the day, you know what I'm saying? I want to keep the blood flowing, okay? So I'm Chris Hughes. I also work for the Energy Conservatory. And what I want to talk to you guys about just real quick is like, who is very familiar with putting in heat pumps? Show of hands, right? Who has not seen heat pumps come to their market yet? Nobody. So everybody's got heat pumps flooding their way. So unless you have been living under a rock, I'm sure you've seen the whole, like, the funding and, you know, the manufacturers of equipment are really pushing for it, right? So we're going to talk about that. So we're going to just jump right into it. So let's get started. Okay. So in this class, there's a couple things about heat pumps that you need to know. And we're going to get into those, and we're going to talk about the caveats of what could go wrong with these heat pumps if you don't install them properly outside of just the equipment itself, right? So our learning objectives today is going to say what's driving heat pumps, traveling through the climate zones, which is going to be fun, and then Russ is going to take us to some stuff about new Manual S. All right, so once again, we're going right into heat pumps. Okay, electrification is all the rage, right? Russ, why is that?
You're just asking me because I'm from California, I think. Yeah, it's a big deal. It's a really big deal. I mean, there's the ones you hear about all the time, the environmental stuff, the greenhouse gases, you know, the fact that they can be powered by sustainable energy sources, PV and wind power and all that good stuff. That's all wonderful. I'm a mechanical engineer. I have 35 years of designing residential HVAC systems. And my entire career, gas made me really, really nervous. To me, the biggest thing is safety. The difference between, you know, how many news articles do you read about heat pumps blowing up and, you know, people dying from the gases that heat pumps give off and stuff like that. So that's always been a big thing for me. So that's what's pushing it. Not to mention the fact that the government is throwing millions and millions of dollars at these things to try to get you to install them. That's probably a big push as well.
So just kind of throw some fun slides at you. So we're after the decarbonization goal, right? And what's being pushed down our throat is to reduce the furnaces and bring in the heat pumps, right? So we can do that. Steve, tell us about this money, this Inflation Reduction Act.
Okay. So there's money coming, lots of money, but it's going to be up to each state how they're going to give it out and how they're going to incentivize people to put in heat pumps. So I want to echo something that I heard from Ty Brannaman, and that is, if you're not a big believer in heat pumps, it is absolutely your choice to just stay away from them. But there's a lot of money coming, and if you want to take the money and you don't want to piss off your customers, then you should know how to do it right. And what are the potential pitfalls? What are the things that could cause a well-intentioned install to go wrong and not deliver what it should?
Okay, so let me ask you a question. Is anybody taking advantage of the rebates right now? Any show of hands? So not a ton of y'all yet. So obviously well, yeah, I know about yours. So like, you know, be on the lookout because it's coming. There's a lot of incentives, right?
I think only a few states are actually hitting the street yet. They're still trying to figure out how to do it.
Yep, they're still trying to. What's that?
Is Florida in the game?
Is Florida in the game?
Yeah.
Good question. Later on this year.
This year.
Later on this year. All right, so enough about rebate talk. That's not really what this is about. I just wanted to encourage people that's what we're talking about, heat pumps. So it's moving, and we want to try to make sure it's getting done right. So we're going to get technical. All right, so we're going to take a trip across the United States through the different climate zones. And we're going to start right here, right where we're at, right here in Florida, okay? We're in climate zone 2. First problem we're going to talk about that could steer us wrong in doing heat pumps. Russ, we've got 2 techs standing in front of that house right there. It says no load calculation, possible over tonnage, right? Tell us, what are these guys talking about?
Yeah, this is the ultra simplified version. The slightly more technical one is where you have the piece of paper that you cut the shape of the house out of and you hold it up and it says 2 tons, 3 tons, 4 tons. The interesting thing about this, 500 square feet per ton, that's been around for years and years, but what's wrong with that? We're talking about heat pumps. 500 square feet per ton is for air conditioning. It does not work for heat pumps, so even if you are using that, you can no longer use that for heat pumps, okay? So we're going to talk about the difference between sizing a heat pump for heating and sizing a heat pump for air conditioning too. So don't do this. Do a proper load calc like you're supposed to.
So let's talk about a few problems we have with that. Short cycling, right? We've probably all in here been in the trade long enough to know if we over tonnage a system, we're going to have short cycling, right? And what does short cycling do? It's going to leave humidity in our home, right? And we're going to lead to this right here. Probably moldy grills on the inside. Any of y'all seen that? Show of hands, right? How about this one? Who's here from Florida? Show of hands. How many sweating air handlers have you seen, Joel, in your life? Most of them. All right. So there's signs. Let me ask you a question. What other signs other than that have you seen from over tonnage? Anybody care to comment? Come on, Dustin.
Over here.
I know you got one buried. Stayed up too late.
Chris.
Stayed up too late last night, didn't you? Michael?
The insulation ripped off the front panel. The insulation ripped off the front panel.
Insulation ripped off the front panel. Right. Equipment doesn't last. All right. So interesting. So we're seeing it. All right. So, Russ, what's our action item then?
So there's 2 basic kinds of load calculations. There's what we call a block load, and that's the load of the entire house all in one, assuming just one system. If there's 2 systems, then you do a load for one half of the house and a load for the other. But that's called a block load. That's all the rooms added together. That's fine for sizing the equipment to meet the total load of the house. Okay, very easy to do. In that situation, you've got 4 walls, a ceiling, and a floor, some windows. Really easy. You can do that on the back of a business card. Okay. But if you want to do any kind of airflow to rooms, if you want to know how much air is going to this room, how much air is going to that room, you have to do a room-by-room load calculation. Now you've taken 4 walls and you turned it into 1, 2, 3, 4, 5, 6, 7, 8, 9 walls. And however many rooms there are, each room has a ceiling. So you're doing a load calc on each individual room. You add those all up to get your block load. But if you want to know how much air to send to each room to size your ductwork, you have to do it room by room. And once you do that, it's actually fairly simple. And I'll actually be talking about this on Friday, is if that one room is 10% of the total load, it gets 10% of the airflow. So if you're moving 1,000 CFM, that room's 10% of the load, it needs 100 CFM. And you just do that for each room. Now you know how much air each room needs. Now you just have to size the ducts accordingly. So block load versus room by room loads.
Yeah, and I like to just add to that as a contractor. Like if I know my customer's really not into wanting to spend money for me to investigate, the reason we're saying block load and room by room load, I may go block load, right? I'm getting a manual J done. I could get the tonnage fast. I'm not spending a lot of time. But if you've got a problematic house and you know your customer's about to spend some real money, you may want to commit to go to room by room load, right? Because you know you're probably going into the full duct design. So something to think about. All right, so we handled up on our load calculation, climate zone 2. Now we're going to take a road trip, and we're going to go over to Steve Rogers' land over here in Minnesota, right? Now we're headed to climate zone 6. Steve, tell us what we deal with in climate zone 6. What are you seeing over there?
In climate zone 6, anybody want to guess what our design temperature is in Minneapolis?
I've got a -20 right here.
Depending which version, it's minus 10 to minus 8.
Way.
Yep.
Is there penguins in there?
We have no penguins. We have some polar bears in the zoo.
Permafrost.
All right, so Steve, you would say that climate zone 6 then is a dominant heating load.
What's that?
A dominant heating load.
Yeah, definitely heating dominated. We actually occasionally have problems of airflow being too high because you have a huge furnace and a small air conditioner.
Right. So just to kind of recap, there's a lot of furnaces up there, okay? Heat pumps haven't quite made it there yet. They're coming.
It's all
but
furnaces.
It's all furnaces. And what do we know about furnaces, Steve?
Well, we know that with furnaces, we can deliver a lot more BTUs with less airflow. But even in Minnesota, we're going to get heat pump incentive money.
Right. So incentive money is being pushed to the homeowner. They're incentivized to say, oh, maybe I want a heat pump. But you're at Steve Rogers' house, and let's say Steve has all this ductwork feeding in the walls of the house from a furnace that you just learned from Steve is carrying a lot of capacity and a little amount of airflow. All right? And then you've got a homeowner saying, oh, I want a heat pump. Think about that. Keep that in the back of your mind.
And for those of you in the South that don't know how we set up systems in the North, ductwork is usually in the ceiling of the basement, and the basement's often finished. Yeah. So that means if I'm going to renovate ductwork, I'm tearing out the entire ceiling of the basement.
Yeah. No big deal.
Yeah. No big deal.
What do you do? 2 duct systems?
Oh, we're going to find out.
No, you run up a chaser up the walls to the second level.
So the question is climate zone 6 ready for heat pumps? How do we know? Steve,
Okay.
Tell us what we're looking at here.
Yeah, so what we're looking at here, I might need to point on here, but this would be a pretty typical system in Minnesota, and you can see that right here we've got I think I did a 80,000 BTU furnace, and this furnace is already at kind of a high static pressure. It's nearly 0.8 inches of water, just barely under that threshold. We like to keep it under 0.8. But remember, we're in Minnesota, so if we want to install a heat pump, a lot of people are going to try and go with a larger heat pump if they can. So this is an example where we've started with an 80K furnace and we're trying to put in a 4-ton heat pump, whereas for cooling, it maybe only had a 2.5 or a 3-ton cooling system. So what does that mean? That means instead of having, about 1,200 CFM that you'd need for the heating load, now we're trying to push 1,600 CFM through the same duct system. We just explained that duct system is not easy to change like it is in an attic. And so what's going to happen is it's going to depend on what kind of motor you're replacing it with. If you replace it with a PSC motor, the motor's not going to be able to keep up and the airflow is just going to take a nosedive. You're going to end up with way too little airflow. And so your static pressure won't be off the chart, but it'll be higher and the airflow will be way too low. Now you're facing a situation where there's so low an airflow that the system might be locking out on high head pressure. And that leads to what? Resistance heat. Okay, we're not now meeting the reason that we put the heat pump in the first place. So we'll advance to this next slide here. So this is a similar example. Yeah, so this is not going to work. There's not enough airflow to have a heat pump working properly because we put in a heat pump that might not be too big for the house, but it's too big for the duct system. And we can tell that if we test the airflow first.
Just want to add, that's a test example with a PSC motor.
Yeah. So here's the next example. The next example is...
What app is that?
That's the TrueFlow app that we're showing.
The TrueFlow app. You can see that the TrueFlow device here, this is what we've used to test the airflow, but you can test airflow other ways. There's not the only way to test the airflow. So this is the same example. We're starting from the same system, but let's say the heat pump we put in is a modern heat pump with an ECM motor. Now the ECM motor, what happens when it faces more resistance from a duct system that's too small? It just pushes harder. So in this case, we're able to get enough airflow. You can see that our new system is going to have airflow in the green, but the static pressure is off the charts. And what happens when the static pressure is off the charts? We got problems. It won't be a problem with the compressor and the outdoor unit. Here the problem is with the indoor unit and the blower fan. Blower motors don't like to operate. at 1.3 inches of water all the time.
So let me ask you guys a question. What do you think is more important, airflow or less airflow to keep the static under control? Would you rather control the static pressures on the unit, or would you rather maintain the proper amount of airflow? Anybody want to take a stab? What's that? Trick question? So I'll go ahead and say it. You want to maintain the airflow, right? Because you want the system to try to deliver what the house needs, right? Let the equipment suffer first. Don't break the house. That's like my golden rule. Like, I want to move the proper amount of airflow. Am I going to have equipment failure problems? Maybe a motor that's going to die or something like that? Yeah, but I don't want the house to start growing mold or having other issues.
So, want to replace a blower motor or replace a compressor?
Yeah. Right. All right, so moving on. So what's going to happen if we installed a heat pump on that system right there? Steve?
Yeah, so what's going to happen is we're going to get the high static pressure. That chews up a lot of electricity, and very likely you're going to be looking at ECM blower motors burning out. You guys have probably heard people talking about, oh, these new ECM motors, they just don't last. Okay? A lot of the time, the problem is nothing to do with the ECM motor. It's that it's running at 1.3 inches of water, and it can't handle the heat. It can't push that hard for very long. So you're losing money, and not just in more electricity to push the airflow through, but also you're probably going to burn out motors.
Right, so we have a heat pump. It's struggling against bad ductwork. What's that heat pump going to do in cold weather? I'm looking at you, Adam. You should know this answer. What's going to happen to that heat pump if it can't move the air? It's going to trip on high head pressure, right? And then what's going to take over? Resistance heat. Is resistance heat cheap to run? No, it's not, right?
So so a better solution, rather than trying to put in 4 tons to cover your entire heating load, would be much better to put in a dual fuel system so that your backup is now gas, which is not expensive to run, and it can actually work with the duct system that's there.
Right.
You might need a 2.5-ton system instead.
Let's talk about another complaint, Steve. Let's talk about stratification problems.
So in a lot of great rooms, if we've got a furnace that's oversized, so it's cycling short, airflow is too low on the furnace often, that means we're delivering really hot air for not very long, and in the 2-story great room, it all hangs out near the ceiling.
So this is a fun slide for me because I learned this trick on a church job me and my dad did, and I learned from an engineer that when I would get air over about 98 degrees, it would heavily stratify fast, which means all the hot air would go up, all the cold air would go down. And then he told me everything he would design, when he would design commercially, he would try to maintain about 95, 98 degrees. And I was like, why? He's like, so I don't stratify the air. So that's a little tip for you guys. So like if you're dealing with stratification problems, if you keep your output temperature lower, you'll have less stratification problems. It's pretty cool.
And if the output temperature's lower, it's going to run longer, which also helps with stratification.
Yep, more airflow. All right, so we covered that, motor complaints, right? We don't want to eat up our motors. Right, so what's our action item? We need to check the sizing of our duct system. Right, if we're going to go into heat pumps, we need to make sure our ducts are big enough.
Yeah, so the action item here is to measure the airflow, check the sizing of the ducts. Now, this example in Minnesota assumes we learned our lesson from the first city, and we actually did a load calc on this house. We came up with the right size system, but it was too big for the ducts.
All right, so we did a load calculation. We've checked our duct sizing, and now we're going to travel to the great state of Texas. Anybody from Texas here? Where's Regan? Where's Regan at? Thought I seen him. He'll love this one because I pulled this meme from him.
Yeah.
Load calc's done,
Everything's
right?
bigger in Texas.
Everything's bigger in Texas, including the duct leakage to outside. Steve,
Okay.
tell us what's going on here.
So I'm going to tell you about duct leakage to outside. Many of you have heard me talk about this in years past, but what I want you to get out of this, just if you remember one thing about duct leakage to outside, remember this. It's a double whammy. So let's say you've got a lot of duct leakage in your attic. Let's say you're leaking a quarter of your capacity. So now I've got a 4-ton system and I'm losing a quarter of the capacity because it's just blowing into the attic. That means that I'm only delivering 3 tons into the house. Okay, but something else happened too. That quarter of the air that we lost, it has to get made up somehow. Because if we're sucking more air out of the house than we're delivering into the house from the ductwork, where's the extra air come from? Outside. And what does that do to the load? The load went up. So double whammy. Not only did you lose capacity, you also increased the load. So if we talk about installing a heat pump replacing a furnace, the odds of not being able to keep up just went up. You got less margin for error with the heat pump. And so making sure you get the duct sealed is the only way that you can deliver all the capacity that you created into the house, and that you don't sabotage your load calc by adding a bunch more load that you didn't account for. You can do a great job with the load calc, but if you have duct leakage to outside, that's something manual J can't predict.
Right. An engineer once told me 1 CFM equals 1 CFM out.
Yep.
Steve, maybe you might have told me that.
Yeah.
You said houses are
well,
squishy.
there's a real easy way to know if you've got 1 CFM coming in for every CFM going out. Okay, if you watch the house very carefully and it doesn't implode, then the airflow in equals the airflow out.
I got a question. So, can you hear me okay? If you got all this supply leakage and it's causing all this imbalance, can you fix it by poking holes in the return duct?
It depends on what you mean by fix it. It will balance the pressure in the house. It will not balance the load.
Got it. Okay.
So let's talk about this. So what's going to be our comfort complaint? A system that's not able to keep up, right? We're going to end up with, if you can see in that slide, I don't know if you can see it good, but we've got some red zones, we've got some blue zones, and we end up with this situation. So bonus round. Who can tell me which room has the most potential leakage outside in that situation? Adam McCoy in the back. Room 2 if it's in the summer, the most leakage. Interesting. Anybody else? Room 2 in the winter. Steve, you want to take it?
Yeah, I think they're both right. It depends. We didn't specify if this is winter or summer, right? Okay. But the important thing to recognize here is when you depressurize the house and you're sucking in a bunch of load from outside, that load is not evenly distributed. That load's going to happen wherever there's more leaks. And if you're in heating season, you're sucking in at the bottom of the house. And if you're in cooling season, you're sucking in at the top of the house. That's just how the stack effect works out. Because you gotta have air flowing in and out typically, unless it's really bad, then you only have air sucking in through the whole house. But in either case, that's going to cause a pressure imbalance because you're going to add that extra load from sucking air in wherever the leaks are.
Let me ask you a question. Does this feel building sciencey yet, or does this feel air conditioning? Show of hands. Does this feel like air conditioning? Raise your hand. Or do you feel like this isn't something you should have to worry about and this should be the building science guy's job? Raise your hand. Raise your hand if you want to stand up and play the game of crisscross jump. Come on, guys. Here we go. So what's our action item? We need to check for duct leakage to outside, right? If our ducts are not tight, our heat pump is not going to perform properly.
Yep. Can't keep up, runs the electric resistance, big power bill. And who are they mad at? The heat pump manufacturer? No, they're mad at you.
Who gets the first phone call?
Yeah.
Air conditioner guy. All right, so here we go on our journey. Now we're headed to Zone 5, Washington State. This one's fun.
Okay,
We're going to
Seattle
talk
house.
about a proper control strategy, right? When do we need to kick in our resistance heat? Or when do we need to turn on our phoners? Or do we not even need to do that, right? Very important. So Steve, when do we need to turn on our resistance heat? Let's say we've got a heat pump with electric resistance. What do we need to do?
So we need to know a few things about how this system pencils out before we can figure out exactly how to set our controls. But just to review, remember, we've done our correct load calc. We made sure the duct system is okay. And we've made sure there's not massive duct leakage to outside. But we could still screw it up with the controls and make the customer really unhappy. So this is about how do you set the controls. So let's look at the next slide.
All right, so first thing we need to know is heat pumps do not freeze at 32 degrees, right? So who knows when they like to do their swap over set point on their heat pump? Anybody? Who does it at 35 degrees? Show of hands. Who does the 35 degree swap over set point temperature? Who does 30 degrees? Who does 25 degrees? 20 degrees? 15 degrees? 10 degrees? 5 degrees? 0 degrees? -5. Who knows how they should set that set point? Manual S. All right. Steve, when to make the switch? So in this example, we've got a heat pump and we've got resistance back heat. We want to determine when we want to make that swap over.
Yeah.
First thing we need to know, Russ.
Load calcs. So this is a screenshot of a ACCO-approved manual J load calculation. On the left side, you see the heating loads there, and then it's broken down by building components, and then you got the total at the bottom. On the right side, that's all your air conditioning loads. Same breakdown, but then you got all your sensible and your latent and all that other stuff. So what we're looking at is the total heating load on that side. Up at the top, what they will typically show you is what's called a delta T. All right, and that's what drives heat through a surface is the delta T on either side of that surface. So it doesn't matter what your outdoor temperature is and what your indoor temperature is. What matters is the difference between those two numbers. If they both go up and down, your delta T, the difference between those two numbers stays the same, and the heat transfer stays the same. Okay?
Is that why you save money if you set your thermostat lower in the winter?
It's possible, yes, it is actually.
Say that again, Steve. We couldn't hear you.
Oh,
So
is that why you save money when you set your thermostat lower?
you reduce your load because you're reducing your delta T. You're making the indoor temperature closer to the outdoor temperature and changing your load. But that's not what you size your equipment to, but that's how you can operate it that way too. And so down at the bottom is your total load there. That's the number that you want. That's the demand of the house. Now your job is going to be to pick a heat pump that will provide that much. That's how much heat, how many BTUs that house is losing in an hour to the outside. And if we just let it leave, the house gets colder. So we have to replace it at exactly the same or about the same rate that it's losing. So it's about supply and demand. This is our demand. Now we have to determine what our supply is that our equipment gives us.
All right, so let's keep going. So we've got some action items here. Go ahead, Steve.
Okay. I want somebody who's really good at reading to read this word for me. Worksheet.
Worksheet.
Okay, this is right out of a Bryant manual. This is a worksheet. Chris and I went through, unfortunately, we couldn't find good instructions for the worksheet, but I can tell you how to do this worksheet. The first thing you got to do is figure out which model of those, there's 4 different model numbers on there, and this is a graph that's telling you how much capacity you have at different outdoor temperatures. So don't be too confused. It's just the outdoor temperature in Fahrenheit, and then in parentheses is Celsius, so just ignore the part in the parentheses. But because of the duct system in this Seattle house, we had to choose the 2-ton system because that's all the airflow that we can move. We had a furnace in there before, the ducts were not that big, and so we're choosing the 2-ton unit. So I've highlighted in yellow the 2-ton unit. The next step is we want to take that point that Russ just gave us from the worksheet, and it told us at what outdoor temperature we have how many BTUs. So this point right here is about 31,000 BTUs at an outdoor temperature that works out to about 28 degrees Fahrenheit. That's our design temperature. That's our design point in Seattle. Okay.
So, Steve, still don't know what I need to do here. What do I need to do next?
Keep paying attention. We'll get there. Okay, so first thing to notice is that dot above or below the line, the yellow line? It's above. What does that mean? It means our heat pump cannot provide that much heat at that temperature. Okay, so we know something, first of all, and that is this is going to need auxiliary heat. Okay? So, but how much auxiliary heat and when is it going to kick in? This is when we start talking about So we were really good at reading the last number on here is, or the last word on here is worksheet. What are the first two words? Yep, this worksheet is how you find the balance point. So next step, I want you to draw a line. Tell me if you're good at drawing lines, straight lines with a ruler. Can you guys do that? This is not hard.
Okay, Steve, I think you need to explain this one.
I will.
You've got a line going all the way across the map in a different section, and it's landing at 60 degrees.
Yeah. So
Why are we landing at 60 degrees?
Right, we got to put our ruler on two different points. And the first point is this one here, the design load calc point. That's the first point. The other point you want to draw your line through is 60 degrees at zero load. Anybody know why we would pick 60 degrees at zero load?
Anybody want to take that one?
Adam's got it.
Adam?
That's when you would start seeing a heating demand or like the switchover point.
Yeah.
Adam says that's when you start seeing the heating demand.
You may have noticed in your own home that on a night, if it gets down to 62 degrees at night, your heat doesn't turn on. Why not? If you're set for 70 and it's 62 at night, why doesn't your heat go on? Yeah, outdoor. The heat doesn't go on in your house when it's 62 degrees outside because there's some heat sources inside the house that provide a little bit of heat. Your refrigerator's always running. You probably got a computer. The people give off a little bit of heat. You know, if you got a water heater inside the house, that's going to always be throwing off a little bit of heat. So all those heat sources add up to be a little bit of heat so that your furnace doesn't go on as soon as you get below 70 if you're set at 70. So this is an average. Most houses in America, typical construction, the furnace is going to, or the heating system is going to start to kick on when it gets to about 60 degrees. So that's where we need zero. We just barely start to kick the heat on for a few minutes at the coldest point of the night when it's right around 60 degrees at night. So that's why we draw the line through 60 degrees at the bottom of the graph and through our design point, and then that's the straight line. So now we have a line that tells us not just how many BTUs do we need on a design day, that's the red dot, but this line tells us how many BTUs do we need on any other outdoor temperature.
Steve, question.
Yeah.
So I think what you're telling me is where those two lines intersect, that's where my heat pump's not going to keep up. So that's when I need to swap over and go all electric resistance, right?
Okay, you got the first part right, the second part wrong. This point where the load of the house, which is the red line, crosses the capacity of the system, that is called the thermal balance point temperature, if you want to show the whole thing.
Can everybody see this right here? 39 degrees?
Yeah. So on this particular house, we would expect that at 39 degrees, the heat pump's going to run flat out, but it's going to maintain temperature, but it's not going to turn off. It's going to run all night long. Okay? So that Chris got the first part right. That's where my heat pump can just turn up and keep up. Okay, but you don't really want to lock out your heat pump and start using your resistance at that temperature. Why not? Well, when you go below that temperature, there's still a lot of heat that heat pump can put out. Okay? Also, I want you guys to tell me, how low can that heat pump go? Look at the chart.
All the way to the flow?
Where does that line end down at the cold end?
Sorry.
Yeah. It's at minus, or 0 and -5. So this particular heat pump can be used below 0 Fahrenheit. Okay? So if I'm setting up the controls, I'm actually going to set that lockout where I'm actually going to not run the heat pump at all way down there. There's no reason for it not to run at a temperature above that. The manufacturer told us it'll run down there and provide some of the heat. But that's the key thing, is it will provide some of the heat, but you've got this area in here where it's not going to provide all of the heat that you need. And that's when your auxiliary heat is going to kick in. the way that it's drawn here, we've got the auxiliary heat and the heat pump running at the same time. So we're talking about resistance heat strips here. If you've got a dual fuel system, you can't do this. You can't run a gas furnace and a heat pump at the same time. That doesn't work because you got the hot air entering the heat pump and it doesn't pump heat the right direction. So what I would do if I was setting this up, I'd set my controls so that I don't lock out that outdoor unit until it's way cold. But I might use this balance point temperature to say, I really shouldn't be using my resistance heat above that temperature. Because if you've done a few load calcs and then looked at how some systems run, you know, this load here from Manual J, it's a little generous. You know, you're probably going to be able to run a little colder than that.
Well, Steve, let me ask you a question. Is that line always drawn to 60 degrees?
So if you want to get real nerdy about it.
Do y'all want to get a little nerdy? Oh, yeah. Let's make it weird.
Okay. So I went to the Passive House conference last year. Anybody ever heard of Passive House before? I know Adam has. So a Passive House is a super energy efficient house built to a German standard for super nerdy energy nerd Germans. But the important thing is they have data on where does your furnace turn on in a passive house, and in a super energy efficient house, the furnace doesn't turn on, or the heating system doesn't turn on until it's around 52 degrees. Yeah. Oh, that's just the heat from the occupants or the refrigerator. Yeah.
Does everybody follow that? Right? If we draw that line at 52 degrees, we're going to change our balance point. Right? It's going to change everything.
Yeah.
So this isn't like every unit you should do it exactly the same way. But it's a good starting point to have the concept down. You with me?
And as long as we're being a little nerdy, one thing to keep in mind is that this line is for the nighttime. During the day, you have less load because there's sun shining in the windows and sun shining on the house, and that keeps the house warmer.
So I want to get a little bit deeper into that, but I'm going to wait till another slide. All right, so one thing I want to talk about. As you heard Steve say, you can run your heat pump and electric resistance at the same time. Why can you do that? Because your heat pump is heating the air, and then you have your resistance heat after it. In a dual fuel scenario, you can't do that with a furnace, right? So, just something to think about.
Because your furnace comes before the coil.
Right, you don't want to blow
You're blowing hot air into
furnace heated air right into your heat pump coil. Okay, so my action item for you. Although we went over the balance point worksheet, a lot of thermostats today are going to have capabilities to kind of take care of some of this stuff for you. So if you're like worried about where do I set this, you could set an action item like setting the droop. What is the droop? Right, I think I'm hearing the answers coming in. It's like when your thermostat sees that loss of temperature, you can have it do the swap over for you. So you don't have to necessarily sit there and work that worksheet, right? That technology has gotten to there. So remember that. If you're worried about doing the math on the job, digging out the balance point worksheet, I mean, it's good stuff to know, but you could set the droop and let the thermostat take care of it for you.
So the droop is a really good way to set it, but let me make another suggestion. I don't know how many thermostats can do this, but I had a heat pump in Minneapolis. I had a dual fuel system, and it heated my house just fine down to 15 degrees. And we spend a lot of hours at 15 degrees in Minneapolis.
Hold on, we got a question.
Package heat pumps. So basically, all my heat pumps are set at 30 degrees, switching to electric.
Say that one more time.
All my heat pumps, electric kicks on below 30 degrees.
All his heat pumps, you do all package units. And you're swapping over to resistance heat at 30 degrees? At 30 degrees.
What?
He's saying the manufacturer. So I got Frederick heat pumps, which Frederick thermostat, but there's no way I can switch where the electric kicks on with these thermostats.
Interesting.
Oh.
So we've got a manufacturer that will not allow you to change the set point to swap over, and it's set at 30 degrees? All right, we need to do some digging there.
Yeah.
So let me make a suggestion of, there's another way to do this, at least with the Ecobee. That's one I'm familiar with. I'm not familiar with many stats. But you can make it switch over when it droops 2 degrees or 1.5 degrees, but there's another way you can do it, and that is if it runs for 90 minutes and doesn't satisfy, then it will kick on the auxiliary. And in my house, I found that it would run for 90 minutes without satisfying and kick on the auxiliary, and I've only dropped like 3/4 degree. So it provided better comfort. I was, not drooping much at all. But if you haven't satisfied after 90 minutes of running flat out, and this is a single stage heat pump, then it ain't gonna get there. You're gonna need some auxiliary.
Yep. So let's recap, right? So what is our 4 action items that we need to handle going into making sure we get heat pumps right, whether we put them in the south, in the north, wherever they go, right? We need to do a manual J&S. We need to confirm the duct sizing. We need to check for duct tightness. And we need to set our controls properly. All right, before we jump into the next topic, does anybody have any questions? I've seen one hand up over here.
If you install an outdoor thermostat in a proper location, break your heat circuit or controls, then it can't come on to the outdoor thermostat lets it.
This gentleman saying he could break the W circuit. Man with the package unit. Yeah, do you hear that? All right, we'll get y'all connected later on that. Good idea. All right, moving on. All right, who's heard about new Manual S? Got a few hands. Who understands what Manual S is? Show of hands. Who's sat in Ed's class? Where's Ed? Who knows who Ed Janawak is? I feel sorry for some of you. All right, so this one goes out to Russ King. Russ, why don't you take a minute and tell us about this new Manual S and the Baby Bear climate?
Awesome. All right, so if you look at your Manual S book, there's 2 main parts to it. The first little sliver is called the normative section, the N sections, letter N. Normative basically means it's like code language, okay? It goes through the full ANSI review process. It's very closely, people fight over periods and commas and stuff like that, and they finally approved it, and it's good to go. All right, and so they've rewritten the normative section of Manual S. That's the rules that tells you how you should properly size equipment, okay? And Wes, is that available now, or are we still? Close, okay. Very, very close, okay. And so we're also, and then the rest of Manual S is what's called the informative section, and that's all the user's guide, how to apply it and things like that. And so we're in the process of formatting that and getting ready for that. So, but the important part is essentially done. And what they've done is they've really looked closely at heat pumps and how people have been using heat pumps and how the technology has changed and all that good stuff. So I've been doing residential design since 1988, manual JS&D, and 99.99% of the systems I designed were gas furnace AC in California and Nevada, okay? Horizontal units in the attic, all single speed. I mean, we didn't even know what a variable speed furnace, a fan was for years and years, and all the ECM motors, those came out, late, in the process. And back then, even when you size the heat pump, standard practice was you size the heat pump to the cooling load, then you look at your heating capacity and your heating load, and you said, well, I've got to make up that difference, and you would just use that heat strips, okay? That was standard practice. That's just how you did it. Well, the problem with heat pumps is you're buying one piece of equipment that's going to give you a certain amount of heating and a certain amount of cooling, and that's it. You cannot mix and match those like you can a furnace. With a furnace, you can buy an air conditioner that gives you a certain amount of cooling, and then you can pick a furnace that gives you all different kinds, big furnace, small furnace, whatever, and you can mix and match. Well, you can't do that with heat pumps. That's the biggest challenge, and this is something I've learned in the last couple of years. is it's a real challenge. It's a real challenge. You've got a fixed amount of cooling and a fixed amount of heating, and you have to make that fit to your loads that could be all over the place, depending on your climate, okay? So to keep it simple in my mind, I came up with the 3 bears, okay? Mama bear, Papa bear, and baby bear climates, okay? So there's different kinds of climates that you have to deal with to make this fixed relationship of heating and cooling fit to these climates. So mama bear, mama likes it hot, okay? She likes to wear a bikini. She likes it hot. So that's going to be Las Vegas, Phoenix, Florida, okay? Mama likes the hot stuff, all right? So those are climates that are cooling dominated. Papa's the opposite. He likes to put on his down jacket. He likes to be where it's cold, all right? He's a polar bear, so that's going to be a heating dominated climate. So your heating load's going to be up here and your cooling load's going to be down here. Mama bear, you're going to have big cooling loads and low cooling loads. And then you got the baby bear climates where they're both right about the same. That's like the, perfect, the baby bear climate. So the nice thing about the baby bear climates is the heating load will match the heating capacity, the cooling load will match the cooling capacity, and it's very easy and off you go. So we're not going to deal too much with those. Those are easy, all right? What if you're in the mama bear climate, you've got a really high heating load and a really low cooling load, and you've got a heat pump that gives you a fixed amount of heating and cooling? Do you size to the heating load, or do you size to the cooling load? You can do either. So let's talk about that. All right, so on the left is your load. That's the house. That is driven by the climate. So this is a baby bear climate. Your heating load's not that much. Your cooling load's okay. They're kind of close to each other. And as it turns out, that's kind of how heat pumps look. Heat pumps, that relationship between heating and cooling is always about the same. It goes up and down with climate, okay? But it's always about the same. In a baby bear climate, your load matches your capacities. It's great. Off you go. So you'll see that the red on the right is just a little higher than the red on the left. So that means we're sizing to our heating load. It meets the heating load. We look at the cooling load. It's a little bit higher, but not too high. Not too high. So in that case, it's easy. That's easy. All right, next slide, please. So now we're going to go to a mama bear climate. And a mama bear climate, maybe Texas isn't the best example of a mama bear climate, but it's cold winters, okay summers. So it's going to be a heating-dominated climate. Sorry, no. Hot summer, other way around. Yeah, I keep screwing it up. Hot summers, okay winters, mild winters. So on the left is your load. That's the house. The cooling load is really high. The heating load is relatively low. But then you take this fixed relationship of your heat pump capacities and you try to match it. So this first one is size the heat pump for the cooling load, which may cause the heating capacity to be oversized. All right? So that's a problem. That's a problem. Now this is a single stage piece of equipment. The nice thing is now we have variable speed and 2-speed equipment, okay? So you've got now that heating side of the heat pump can act like a smaller heat pump and be appropriate for your lower heating load. The new Manual S takes this into account, gives you guidance for what's too big, what's too small, and which you should look at. So what if then you were to size the heat pump for the heating load? You pick a heat pump where the red on the right is just a little higher than the red on the left, so it's got enough capacity to meet the load, but you've got that fixed relationship. Your cooling can only go so high, and it's not going to work. It's not going to be big enough. All right, so that situation, it doesn't work. So now we're in the Papa Bear climate. The Papa Bear climate is Steve's climate, way up there. It's got very, very cold winters, not so hot summers. So look at the loads. They've switched. Now the heating load is the bigger one, and the cooling load not so much. And then you've got to make this fixed relationship of capacities meet those. So what do? What do you sacrifice in order to make that work? So in this case, we're going to size it to the heating load. We're going to look at the heating capacity of the heat pump and the heating load and make that work So you'll see that there's a check mark there. It's just a little bit higher. But the cooling load is way too big. And what happens when you oversize on the cooling? You get short cycling, you get all these other problems, okay? So that's a problem. But that's a single speed piece of equipment. You've only got one choice. If it's a variable speed or a 2-speed, you've got this lower option to look at, okay? And in this case, it's actually, even though it can go down, it doesn't go down far enough. So it's still a problem. So that difference is a percent. Manual S will give you guidance on what that percent should be of oversizing. So you've just kind of got to make it work. You got to look at the different pieces of equipment that you have to work with and make it fit. And Manual S does a really nice job kind of walking you through that. There's about 9 different options. You've got your dry climates, you've got your single speed, you got your variable speed, you got all these different choices to help you pick a piece of equipment that's going to meet one of these scenarios so that it'll work in the winter and work in the summer. In this case, we tried to size it to the air conditioning load, and then we know for sure it's not going to meet. So this is actually the old way of doing it, right? You would size to the air conditioning load and then make up the difference with electric resistance strips, all right? There's a lot of places now that are trying to really discourage electric resistance strips. They're trying to get it to size the heat pump purely to the heating load, okay? And we can do that now because we've got the multi-speed air conditioner that can act like a big air conditioner when it needs to or a small air conditioner when it doesn't need to. You saw that graph, you saw the balance point diagram with the dot and you drew the line down to 60. That dot came because you did a load calculation. If you don't do a load calculation, you don't know where to put that dot. And if you don't know where to put the dot, you don't know where to draw the line. If you don't know where to draw the line, you don't know where to set your override, all your other stuff. So it's very, very important to do a load calculation. I can't emphasize that enough. I've spent a lot of my career training contractors how to do load calculations. And we'd sit through a 3-day class, and they'd walk out at the end of the day, say, Russ, great class, but there's no way in heck I'm going to do this. Takes too long. Takes too long. Nobody's paying me to do it. Forget it. Ain't going to do it. That's bad. All right. I've resorted, in this late in my career, I've resorted to shaming contractors. We have a little sticker that says, do you even load calc, bro? Right? We have a little sticker. Come by our booth tomorrow, on Saturday and pick up a sticker. The other thing I like to say is if you're a professional carpenter or a woodworker or a framer, what's their famous saying they say about measuring? What do they say? Measure twice, cut once. If you're a professional carpenter, you measure twice, you cut once. I'm not a professional carpenter. I measure once. I end up cutting twice, but that's okay. I'm not a professional. If you're not doing load calcs, you're not measuring at all. How can you call yourself a professional if you're not measuring at all? You're guessing. You're guessing. All right, so measure twice, do a load calc, double check your load calc, and then do it right.
All right, there's something I want to talk about, then we're going to open it up for some Q&A. So what Russ is talking about, load calc. So I'm going to humble myself for a minute and say I went the way that you probably shouldn't go, which is I bought the load calculation software and was like, oh, I'm going to figure out how to do this without reading manual J, S, and D. And I thought, oh, well, the program will teach me. I'll kind of teach myself. I'll figure it out. It took a long time, and until I picked up the manuals, the ACA manuals, and read them, then it kind of brought everything full circle. So if you're not doing load calculations right now, let me give you a tip. Read the ACA manuals first, then go chase down your software. Don't do it the other way around. Don't expect your load calculation software to teach you what's in the ACA manuals. It's a tool that helps you apply the principles from the books. It's not going to teach you the manuals for you during the software. That's been my takeaway from having to go through the painstaking valley of that. All right, so we've got just a few minutes. Do we have any questions? Kimberly in the back.
Hi, Kimberly Llewellyn with Mitsubishi Electric. I wanted to go back to the Climate Zone 6 heat pump section a little and make sure that we're being clear. We don't need the slides, but just back to the subject. We're being clear that with variable capacity heat pumps, there are cold climate options that can deliver the rated capacity all the way down to -5, -10, -15 degrees. And if you're in a climate zone 6, you want to make sure that's the system that you're choosing if you're doing an entire system change out. Now, I'm not advocating for that, and I'm not saying that's always the right solution. About the static pressure discussion, it's really common that we come to find out that we haven't done a good enough job training or installing contractors to know that there are static pressure settings that can be chosen in order to sometimes adequately address existing ductwork. So those are just 2 points of clarification.
Thank you, Kimberly.
Thank you again. My name's Efren with HVAC Tactical. But I had a brief little question. Reverting back to the last slide, talking about inverter systems or multi-capacity systems. Correct me if I'm wrong, but I feel like single-stage systems and two-stage systems are slowly going to become obsolete. Is there no point in really pushing them as hard as they were once pushed? Or is multi-capacity systems going to start being the future?
I think it
That's a
depends
good
on your
question.
climate.
The question was, if I recap this right, is inverter-based equipment going to take over the single-stage, two-stage market? Yeah, to do better HVAC, right? That's the question. That's a tough one. I think I heard budget. Budget's always going to come into play. So do I think it's going to go away? No. Do I think it's going to become more prominent? Yes. I think so. There is some pretty interesting. Kimberly? What percentage of the market would you say is VRV, VRF right now? Or inverter-based equipment? 10 to 15%. So that's where we're at right now.
But increasing by another about 10%, of the market per year. So it's climbing.
So it's climbing. But do we have another question?
Chris, I have a comment actually on that topic. So it's going to depend a lot on your climate. If you're in a baby bear climate where everything matches nicely, that single speed piece of equipment, the capacities will match your loads and it'll work great. All right? There's going to be situations where your load is such that a single speed simply will not meet the manual S requirements. So what do you do? You can always go to a different piece of equipment. What else can you do besides change your capacity? What can you do? Change your load. Everyone thinks that the load of the house is cast in stone. It's not. Even in new construction, you can say, hey, I've looked at this equipment, it's not working, but you know what? If you put some slab edge insulation on this house and drop the heating load, this piece of equipment will match those loads better. The house will be more comfortable, be more energy efficient. Always consider the other side of the equation, the load. Don't just focus on the capacity. Sometimes it's a tough sell. Sometimes you got builders who don't want to change stuff. Sometimes you got homeowners who don't want to change stuff. But if you get good at selling that and explaining it, you're going to be much better off.
All right, Ed from ACCA wants to add on to that.
Yeah, that's an excellent point when we're talking about new construction. And I want to add from an existing house standpoint. We can add a bunch more insulation. We could potentially tighten the place up.
Seal it up, yep.
And instead of going the route of VRV, and this is as much a question as a statement, in my market, I think I'm going to dissuade somebody from going VRV, put in a single-stage piece of equipment. I got a 4-ton heat pump requirement, 2-ton AC. I'd rather separate the load. I am going to do all my latent with a DHUM, and I'm going to do all my sensible with the heat pump. So I don't know which is cheaper in the long run, but I have my suspicions, and I'm going to keep them to myself.
Allison.
All right, Russ, you said that when the loads match, you can use a fixed capacity piece of equipment and it works just fine. But the design load is not the load all the time.
Correct.
So the variable capacity does help with the loads that change daily and
The part
seasonally.
loads, yes. But well, I guess what I'm saying is the single speed will still meet the manual S criteria for proper sizing. A variable speed might work better in the long run, but the single speed will still meet manual S, yeah. One other thing I wanted to say too, and they alluded to it, HVAC contractors are really, really good at what they do. And there's a great expression, when you're a hammer, everything looks like a nail. You've heard that expression? So if you're an HVAC contractor, every solution looks like an HVAC solution, right? So we're here to become home performance contractors, to high performance contractors, right? Look at the other side of the equation. Everything's not a nail. We need to be Swiss Army knives.
So I think what we're looking for is permanent load reduction is what Russ is referring to. So let me ask you a question. Let's have a little fun. Steve, I'm going to get to you because this is Steve's like one of the best spills. If I want to bring down permanent load, and let's say I want to go after air sealing, where am I going to go first and why?
So if you're not going to air seal?
No, if you are going to air seal.
Oh, start with the lid.
Why?
Because that's, in most houses, that's where there's the most air leakage. So crawl spaces, if you're not slab on grade and if you don't have a basement, crawl spaces can often be pretty bad as well. But start with the lid. If you seal the lid and add insulation in the attic, normally that will significantly reduce your load and increase comfort. So air leakage not only causes these problems we've been talking about with load, but a leaky thermal envelope is just way less comfortable. There's outdoor air leaking in, and you're trying to, sit and enjoy your living room, and, you got hot air coming in the summer, or you got cold air coming in the winter.
So what Steve is talking about is to reduce the amount of flow of stack effect. Steve, tell them what stack effect is.
So stack effect is, we can all imagine a hot air balloon. And this is the best imagery that I can think of for how the stack effect works. A hot air balloon rises even though there's a big hole in the bottom because the hot air inside the balloon is trying to go up. It's less dense than the air around it, and that lifts the balloon. Okay, the same thing happens inside your house in the wintertime when the air inside is at 70 degrees and the air outside is colder. The air still has that same buoyancy. It's just that a house is much heavier than an air balloon. That's why your house doesn't float away. But the air is still pushing up and trying to go out. And so it starts to leak out through the roof or through the ceiling, the highest point in the house, and it leaks in down low. And it does that 24/7, 365. As long as there's that temperature difference, it creates a pressure difference that we can measure, and that's what drives the leakage.
So I really appreciate what you guys have been sharing, and I think load calculations are the way to go. My question is more of a practical, working with the customer question. So if you go out on a replacement call and they have a 3-ton system, you do a load calculation and it says they need a 2-ton system. And they say, no, I want a 3-ton system, man. That's what I had before. I want to make sure this thing's going to work. Well, how do you navigate that?
Are they requesting it to be changed out because it's broken or because there's a problem with it or they're not happy with it?
It's broken.
Okay, so if their 3-ton worked fine for them, then that's fine. I would say leave that in there. But I would also have them sign something saying that you recommended a smaller piece of equipment, and that if it has any of the following problems, moisture removal, short cycling, whatever, that you tried to convince them to put in a smaller piece of equipment. But there's nothing better than data, right? And a homeowner being perfectly happy with a piece of equipment, that's really good data to have, right? So I would say that's okay. But there's a lot of times, where they're here and they're going to say, yeah, I had a 3-ton. You say, well, it really needs a 2-ton. And they may say, well, you know what, that's going to make all our problems worse. And you say, what problems? Well, hot upstairs, cold downstairs, it was different, all this other stuff. And you say, that's because it was oversized. And that going down a piece of size will solve those problems. So you got to kind of balance it out. Yeah.
I'll give a tip to that. So my background's been a contractor before I came to TEC. And when I got into loads and got pretty good at this stuff, what I could tell you is customers love confidence. If you get confident in the data and you present your data well, you will convince that homeowner. They will take your word for it, and you'll stand behind it. And when you exude that in front of them, they will take the bait. I promise you.
I've seen older customers, especially, they're terrified that thing's going to run all the time and cost them a lot of money.
Yeah.
Everybody is. It doesn't matter.
Yeah. So the comment came in as, you know, if there's a way to track down the humidity, that'd be a good way to, you know, sell them on saying, like, I could keep the humidity more in control if I go down on tonnage.
I'd
Let's get
recommend
one
you
more.
listen to the episode on Brian's podcast with Alex Meany and Brian talking about the dangers of swapping like for like. So an old 8-seer air conditioner that's 3 tons doesn't work the same as a modern 16-seer that's 3 tons. You're going to have a warmer coil. Your sensible heat ratio is probably higher. You're doing less dehumidification, even if you swap like for like. And you get comfortable with knowing what those are and being able to explain that confidently to the customer in language they can understand. Like, that's really not a good idea.
Okay, we've got time for about one more question.
Hey guys, so going back to the slide on the Papa Bear climate, I'm doing the sizing for cooling using my heat strips to make up for the heat load. I didn't hear what the new recommendation is going to be. I didn't know if that finished out.
There's options. The reason that we historically did that is because there wasn't a 2-stage on the cooling side that could throttle down to act like a smaller piece of equipment. Now that you have that option, you can start looking at sizing your heating load 100% heat pump and size your heat pump to the heating load and then look at the cooling. It's probably going to be way oversized, but when it throttles down to the low speed, does it come back down within range that's within the Manual S requirements? Manual S now has specific criteria for doing exactly that. Yep.
Awesome. All right, everybody. That's us. Thank you to Steve. Russ, appreciate it.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.